Right. You're here. I'm trying to look for you. All right. Um, I think we can get it started while waiting for other folks to join us. Um, okay, welcome back everyone to our 47th ECS and Cloud Feedback Symposium. Um, Before we start, again, we are going to go through some symposium notes, like especially for those who are new to our event. For today, as usual, we will have three short talks from Camille, Andrew, and Sally. And for each talk, we will have questions after the talk. And in the very end, if you have extra time, we will have a general discussion. If you have any comments or questions, please type them in the chat. Or if you prefer to ask your question verbally, and you can raise your hand and unmute yourself. And we're always looking for volunteers to give the talk. So if you would like to give one, please contact one of our committees. Or in general, if you have any feedbacks or comments to make the symposium better, please let us know. We'd love to hear more. You can always find more informations, including the recordings of all the past talks or the speakers on our website on the Google site. And lastly, today before we start, we have a special call for the IPCC AR7 for related to the climate sensitivity. And Maria is gonna spend 1 to 2 minutes to introduce a little more about this. Take your time, Maria.
Sweet. Thank you. Hi, everyone. I just want to make a very quick announcement that the IPCC next round started to speed up. And now the date for the papers to be allowed to be cited is set, which seems like very far away, but it's actually very soon. If you think like it has to be accepted, so you have to submit much earlier. And there is a little bit of discussion now where to put ECS in the report and how to treat it. So if you work on something which has implications for ECS or TCR, ideally you would quantify its impact at the end of your paper, so it's easier to assess. And then if you have any thoughts on how the IPCC did a good or a bad job in the past to deal with ECS issues, let me know, or Chris Smith or Ben Sanderson. Thanks.
Cool. Yeah, hopefully if you have more questions, you can talk with Maria at the AGU if you plan to go for. So our first talk today is from Camille. And she's currently a postdoc fellow at the University of Washington. As titled here, he's going to talk about the transient evolution of polar amplification under different CO2 rates. Warming.
Thanks, Xia. 1 second. Oh, spoiler. Okay, cool. Can you guys still see my screen?
Yep.
Awesome.
Looks good.
All right. Well, thanks for inviting me to give this talk. Today, I'll be presenting this work that I've been doing in collaboration with Dave Bonin, who's also a postdoc here at the University of Washington. So polar amplification, as I'm sure most people in this Zoom room are familiar with, is this feature where both poles may warm faster than the rest of the globe under anthropogenic climate change. And this is a feature of predicted future climate change as well as an observed signal in the Arctic at this point already. And this has motivated a fair amount of studies looking at and trying to attribute the causes of this amplified warming, particularly in the Arctic, going back even well before this paper, but perhaps most well known in this Piffen and Moritzen 2014 paper. And this paper did this kind of first that I know of this nice type of plot where they introduce how different feedback processes contribute to Arctic warming versus tropical warming or global warming. And this allows you to very easily see which processes contribute to the amplified warming because they lie above this 1-to-1 line. So the kind of earlier work in this field, I think, often focused on polar amplification at a specific time period and made some of those plots like the Pithon and Moritzen plot. But more recently, in the last 3 to 5 years, there have been kind of some interesting works that are kind of complicating this overall picture of the causes and the magnitude of polar amplification. So some of that work has looked at nonlinearities in polar amplification. In other words, its response to varying levels of thing. Other work has looked at asymmetries in polar amplification with respect to forcing direction, so under increasing or decreasing CO2. And then there's also work looking now at, rather than at one particular time period, looking at the temporal evolution of polar amplification across many timescales, ranging from some of these papers looking at the really rapid onset of polar amplification within months or years, to some studies looking on longer timescales. Notably, fewer studies looking at this kind of centennial to millennial timescale on account of how computationally expensive it can be to simulate that. So we want to kind of contribute to this more nuanced perspective of the magnitude and the causes of polar amplification by looking specifically at how the rate of change of atmospheric CO2 forcing can impact the time evolution on polar amplification, with a focus in particular on these centennial to millennial timescales. And the motivation for looking at this question specifically is twofold. One is just based on this kind of intuition that the different components of the climate system all have different response timescales to perturbations. And there's potential for interesting transient climate behavior due to interactions between these different components under different forcing rates, when some components may be more or less out of equilibrium with the forcing. The other motivation is that the historical rate of CO2 increase has varied in the past. So this is showing the year-over-year growth rate of atmospheric CO2 concentrations in observations, but we don't really know what the long-term legacy of these past rates of change or the near future rates of change is on the global climate system. So to answer this question, we're using a series of experiments in the Community Earth System model run under very coarse resolution, where we increased atmospheric CO2 up to 1 doubling from pre-industrial, but using 7 different ramping rates ranging from 4% per year to a 1/16 of a percent per year. And note that the historical increase rates have been kind of between 0.5 and 1% per year. And then after we reach a doubling of CO2, we perform this long integration at fixed CO2 until the climate system reaches a quasi-equilibrium. So then we perform this diagnostic method that I think many people here are familiar with, which is a forcing feedback framework, where we use radiative kernels to estimate the feedback parameters, and that allows us to decompose temperature changes into contributions from different feedback processes and from ocean heat uptake and atmospheric heat convergence. And then we perform this decomposition over the globe and over both polar regions to assess which processes control the time evolution of polar amplification in these different ramping experiments. So here I'm jumping straight to the results. On the left, we're showing the polar amplification factor for the Arctic. And note that this amplification factor is defined as the absolute difference between the polar region and the global average surface temperature changes. And so what we see here is already a very interesting feature, which is that under very rapid increases in CO2 concentration, the polar amplification in the Arctic initially emerges and then disappears and actually goes to zero, so no amplification, for several hundred centuries before reemerging. On the other hand, under more gradual CO2 ramping rates, you have this more smooth monotonic emergence of Arctic amplification. In the Antarctic, we have this interesting feature where there's an abrupt jump in Antarctic amplification more than 1,000 years after CO2 doubling occurs. And this is a huge increase of around 2 degrees that occurs in all ramping rates, although the timing is somewhat affected by the CO2 ramping rate. So already we see that polar amplification has this strong long-term time evolution that is also sensitive to the rate of CO2 increase, even for the same amount of CO2 increase. And now I'll try to explain these two interesting features. So first, looking at the causes of this transiently disappearing Arctic amplification. So I'm showing these sort of Pithon and Moritzen style plots where there's contribution to Arctic warming on the y-axis and contribution to global warming on the x-axis. And here I'm showing 4 different time periods that kind of represent some of the interesting features in both hemispheres, where the increasing dot size shows the progression through time. So what this shows here is, for example, in the most rapid ramping experiment, this is the total warming. This return to the one-to-one line, moving from year 100 to 300, is that feature of disappearing Arctic amplification that we saw on the previous slide. So now in this middle plot here, looking at the gray dots to start, we see that a huge contribution to that relative Arctic cooling is this reduction in the term from ocean heat uptake in the Arctic region. And if we further split up that ocean heat uptake into the contributions from ocean heat transport and storage, we see that's mostly driven by changes in ocean heat transport. So that's the orange dots here, where there's about a degree of cooling in the Arctic due to changes in ocean heat transport that occurs in these faster ramping rates, but not in these slower ramping rates. In the bottom line here, I'm showing the contributions from the surface albedo, lapse rate, and local Planck feedbacks, which are often thought to all be associated with sea ice changes. And we see there's these sort of secondary contributions from each of those feedbacks to this kind of non-monotonic Arctic amplification behavior. So in other words, it seems like ocean heat transports are the primary driver of this disappearing Arctic amplification, but with this sort of support from the sea ice related feedbacks. So let's look at the spatial pattern of the temperature changes in the most rapid ramping experiment centered on that period where we know Arctic amplification disappears. And we see that that cooling that occurs is entirely concentrated in the North Atlantic region. This kind of looks like some of the plots of a North Atlantic warming pole. So I think this naturally leads to the question, is this feature driven by or somehow related to AMOC changes? So here now I'm showing a time series of the AMOC strength for just the most rapid and the most gradual CO2 ramping experiment if you focus on the blue line. And the first thing that jumps out is that the AMOC weakens more under faster CO2 ramping rates than under gradual CO2 ramping rates, even for the same amount of CO2 change. And this was something I wrote about and is its own kind of interesting feature that I wrote about in this other paper. Now in the gold, we see the related ocean heat transport changes. So this is northward ocean heat transport at 60 north. And we see that that too shows the strong dependence on the CO2 ramping rate. So what we think the sort of chain of causality is here is that the AMOC weakens more under faster CO2 changes, even for the same amount of CO2 increase. This leads to a greater reduction in northward ocean heat transport in those rapid ramps, which induces North Atlantic cooling, and then that cooling signal gets further enhanced by sea ice changes and sea ice-related feedbacks, leading to this suppression of Arctic amplification. And this is relatively consistent with previous literature that's sort of shown how the AMOC can modulate Arctic amplification in a variety of contexts. So we think we have a solid explanation for what's going on in the Arctic in terms of its sensitivity to the rate of CO2 increase. Switching now to the Antarctic, in this case, we're interested more in what's going on between the third and the fourth dot. So what's happening between year 1000 and the end of each of these simulations, causing this warming of 2 to 2.5 degrees. So looking again at the contribution from the ocean, we do see this slight increase in the ocean heat uptake term, which is again driven by ocean heat transport, explaining about a degree of warming in the Antarctic. But here in the bottom row, we see the sort of main contribution, which is coming largely from the surface albedo feedback, giving you almost 2 degrees of warming in the Arctic over this period, and then some additional contributions from the lapse rate and Planck feedbacks, again, explaining that jump between year 1000 and the end of the simulation. So again, let's look at the spatial patterns of this warming. So here I'm just showing the change in the surface temperature between year 1000 and the end of the simulation for the fast ramping experiment, but it looks similar for the other experiments. And we see that the biggest change is occurring in this sector in the Ross Sea, which undergoes an abrupt warming. That same region shows a huge contribution from the surface albedo feedback and a very big contribution from the ocean heat uptake term. So this kind of begs the question, do ocean changes cause the sea ice loss that's driving the surface albedo feedback, or vice versa? So let's now look at the total water column evolution in the Ross Sea. So these are the changes over the full water column averaged over that green sector here that encapsulates the Ross Sea. Starting over here at the right, these are the changes in ocean density. So what we see is there's overall waters are getting lighter in time, but around year 1000, the upper ocean actually starts to get heavier until there is an abrupt convective event that re-stratifies the whole water column. The result of that convective event is this upward flux of deep ocean heat, bringing a lot of heat to the surface. And we think the cause of that convective event comes from salinity. So we see at first there's a freshening of the upper ocean, but then again, a little bit before year 1000, that trend reverses and there's this gradual salinification that seems to precondition the water column for this convective event. So we think happens is there's this gradual salinification that triggers this deep convective event, releases a bunch of deep ocean heat up to the surface, which then causes that abrupt sea ice loss and can help explain that abrupt Antarctic amplification. So to wrap up, hopefully I've shown you that the magnitude and causes of polar amplification can have very different transient versus quasi-equilibrium behavior. So kind of looking from those multicentennial to millennial timescales. In particular, this disappearance of Arctic amplification for a few hundred years depends heavily on the rate of CO2 increase because the rate of CO2 increase can really control the AMOC weakening and associated reduction in ocean heat transport. In the Antarctic, we saw this interesting, very delayed, abrupt Antarctic warming more than 1,000 years after CO2 stopped increasing that we attributed to this large-scale ocean convective event. And I didn't get a chance to show it, but I'm happy to talk about it later. But we looked at other models that were forced with an abrupt CO2 doubling as part of long-run MIP or compiled as part of long-run MIP. And some of those did exhibit this signal of transient Arctic average cooling, some didn't. None showed this abrupt Antarctic warming, but very few were run past the year 1000. So we think it's kind of inconclusive whether that event could possibly occur in other models. So I think this kind of adds to the picture of kind of nuanced causes of polar amplification when you consider different timescales, different sort of forcing configurations, and leads to some interesting questions like should we expect a future disappearance in Arctic amplification, or what processes cause this gradual salinification of the Ross Sea that I think are worth exploring in future work. And with that, I'll wrap up and just mention that we have a preprint up for this paper as of last month. You can find it on the ESS Open Archive just by Googling the title of this talk. So thanks.
Thanks, Camille, for the great talk. We have one hand by David. David, go ahead.
Hi, Camille. Nice talk. I have a question. If you draw your circle from 70 degrees north in the Arctic, do you see that same crash? It warms a lot and then it comes back down to zero? Because it seemed like it was all that cooling. It still had Arctic warming, even.
Yeah, you wouldn't get as strong of a signal.
Yeah, but it's there. Yeah.
You would still see it a little bit. But
Okay.
yeah, a lot of that is happening between about 60 and 75 north.
Okay.
Yeah.
And do you have a sense, well, since I'm here, do you have a sense of where this 1,000-year plus time scale comes from? Or I should say, where is the salinification coming from after 1,000
Yeah,
years?
yeah, we kind of debated whether we wanted to try to figure that out because it's kind of hard to track down that
Yeah,
source. But I think there are two main possibilities. One is sort of slow shutdown or slow down of Antarctic bottom water formation, which generally exports salinity from the upper ocean to the deep ocean. So if
yeah,
that's kind of slowing down on millennial timescales, you could kind of remove or slow down the removal of salinity. The other is if the source of salinity from the Atlantic region is changing on a 1,000-year timescale, which could itself be related to AMOC changes or gyre
yeah.
changes. But yeah, it's a tough thing to track down.
Great. Thanks.
Yeah.
Cool. We have a time for one more question. Chris, please go
Yeah,
ahead.
okay. So I was wondering how this then projects onto understanding abrupt 4 times CO2 equilibrium climate sensitivity runs, since it seems like, that's the limiting case of a rapid CO2 increase. What do you
That's
think about that?
That's my whole interest, I think, actually, in studying the different rates of CO2 change is I think the sort of, in my view, the hope with abrupt 4 times CO2 runs, because they're easy to do, is that they can tell you something about the time evolution if that 4 times CO2 state kind of projects linearly onto the sort of more gradual time evolution. What we're seeing here is that that assumption gets broken. And that means that the above 4 times CO2 case might not be able to tell you everything you want to know about more realistic, say 1% per year or slower or more complicated forcing evolutions. So I think that's kind of the big implication of this work that I think is exciting.
Okay, thanks.
Cool. Next, Kevin.
Yeah, following on from Chris's point and your response there, 4 times CO2 is a very large change, and if it happens fast enough, then you get a collapse of the AMOC, and you get this cooling pattern and this change in the polar amplification. But the regime in which there's going to be ambiguity about what we think of as the equilibrium climate sensitivity is going to be in a regime where it will be stochastic whether the AMOC will collapse or not collapse, because then that gives you a very different polar amplification under the two cases, which may be just totally in the noise. And so you'd end up with a situation where, one model run suggests that the climate sensitivity will be high, and another one where it will be low, and you might see a difference of maybe half a degree or something in the ECS if you have a number that a forcing that allows for both a collapse or a recovery.
Yeah, I think I agree with all of that. I think I'm sort of thinking of this as there's a sweet spot of forcing magnitude where you may see these ambiguities either because of the AMOC collapse, or you might see ambiguities with respect to Arctic amplification with relates to the level of AMOC weakening. And I think there's sort of as it relates to this work, I actually took the figure out, but there's a nice figure from this Liang et al. Paper that shows how Arctic amplification is actually lower at 4x CO2 than at 3x CO2, because in that model, 4x CO2 is where you get kind of the strongest AMOC weakening relative to the amount of overall warming. So I think there are a lot of complicating factors in terms of how you use these different runs to estimate equilibrium climate sensitivity, or just what you calculate as your transient climate sensitivity, and how that depends on the rate of CO2 increase and also the magnitude. But I agree, if you go to really high CO2s, then that ambiguity starts to go away because you are kind of guaranteed a certain level of AMOC weakening.
Yeah, I think we have to move on, but there are more questions in the chat and for you, Camille. So thank you again for the nice talk. And next we have Andrea for a talk about the stratocumulus breakup in a warming climate. And by the way, Andrea is currently a PhD student, her last year at Harvard. Andrea, take it away.
Thank you. Let's see. Okay, can you guys see this?
Yep.
Okay, great. Yeah, thank you so much for inviting me. I'm super excited to talk about some work that I just wrapped up with my collaborators, Brian Medeiros, Zhang, and Ellie Zipperman, in which we were interested in characterizing the maximum warming that a subtropical stratocumulus breakup could induce in a warm climate. And so just to get you guys super excited about stratocumulus, stratocumulus clouds are very low altitude clouds and have a very strong cooling effect on the climate. And in this work, we were specifically interested in the subtropical stratocumulus. Here I'm showing you a nice contour map of stratocumulus cloud cover, and I've outlined in black the regions that I'm specifically talking about. And they cover about 6.5% of Earth's surface, and where they occur, they have very strong shortwave cloud forcing, up to about 100 watts per meter squared of cooling. And so clearly, these stratocumulus clouds cover a huge percentage of Earth's surface. They have very strong cooling effect, and so they're very important for Earth's radiation budget. And recent work has suggested using a large eddy simulation that if you go to a high CO2 climate, these stratocumulus cloud decks could be unstable and could break up. And this could cause a very strong positive climate feedback. And this happens because stratocumulus clouds are connected to their moisture source at the surface by convection. And this convection is driven by strong long wave cooling at the cloud tops. And so if you have very high CO2, all of a sudden you have much more long wave radiation coming from the free troposphere, which weakens this long wave cooling at the cloud top. And this could lead to breakup and drying out of these cloud decks. And the critical CO2 where this happens is a little bit unclear, but it's possible that this cloud feedback could be very relevant for both future climate change and also past climates in like warm equable climate states like the Eocene. And because this is such an important positive cloud feedback, the first question that you want to ask is how much warming could a complete breakup of these clouds cause? And so if you wanted to do a simple back of the envelope calculation, you could say, okay, to get temperature change, you have the ratio of the radiative forcing that this breakup causes over the global feedback parameter. And the global feedback parameter, as we all know here, is characterizing how the climate responds to this forcing. So let's say we have these subtropical stratocumulus that cover 6.5% of Earth's surface, and we are taking away their 100 watt per meter squared shortwave forcing, and we assume some global feedback parameter, then you might expect up to 8 Kelvin of globally averaged additional warming due to this cloud feedback. And that's very intense warming. And so understanding exactly how much warming you would actually get is super interesting here. So all of the physics of the climate's response is really wrapped up in this global feedback parameter. And so I want to spend a little bit of time talking about this. So here I'm showing you a plot from the IPCC report, which is showing all of the contributions to this climate, this global feedback parameter. So we have things like the water vapor, lapse rate feedback, our friend cloud feedbacks, which is notoriously uncertain. And all of these things together determine the global climate response to forcing. But so we chose a global feedback parameter of minus 0.8 watt per meter squared per Kelvin, which is on the higher end of what the global climate models are predicting. But what I want to emphasize here is that this global feedback parameter is specific to a CO2 forcing. So what we've done here is we as a community run these climate models under CO2 forcing, which is a pretty homogeneous forcing. And then we study how the climate responds to this homogeneous forcing. But the feedback that I'm talking about here is fundamentally different because we're talking about locally clouds disappearing. And so all of that heating is going to happen in very localized places. And so it's not obvious that the global feedback parameter that we study that is specific to CO2 forcing is a good way to estimate how the climate will respond to a more localized forcing, like a stratocumulus breakup in the subtropics. And so that is the motivating question of this study is how does the climate respond differently to this localized forcing compared to a more homogeneous forcing like CO2? And I think this question ties in really well with ideas like the SST pattern effect, which I think we're thinking about a lot these days. And it'll be important for localized climate interventions like marine cloud brightening. And a big motivation of this study, not just anthropogenic climate change, but also thinking about how past hothouse climates existed in Earth's history. So the method that we used to try to get at this question was cloud locking in CESM2. So what we're doing here is we are hacking the model to impose our own clouds, and we force the model to ignore the clouds that it is trying to make. So here I'm showing you a map of shortwave cloud forcing from CESM2, and you can see that in these black box regions in the subtropics, we have imposed very strong stratocumulus cloud cover. And elsewhere, outside of these black box regions, the clouds are allowed to respond in whatever way they want. So this is our strong stratocumulus case. And then we run another simulation where we completely remove the stratocumulus clouds in those black box regions. So we go from about 100 watt per meter squared of shortwave forcing in those regions to 0. And so our intention was to create this 6.5 watt per meter squared radiative forcing that was assumed in the back of the envelope calculation. But importantly, it's happening in these very localized regions where the stratocumulus clouds exist. And it is the difference between this no strato case and this strato case that will give us the maximum warming that this breakup could cause. And I'll note here that we did kind of the most dramatic case we are imposing stratocumulus clouds that are much stronger than the ones that the model itself makes. But this is hopefully going to maximize our signal to noise ratio and help us say something about maximum warming for this breakup. So in the end, we ran 5 simulations. The first is just an abrupt 8x CO2 spin-up where we allow all of the clouds to evolve freely. And the reason that we did this is, one, we wanted to have some baseline case to explore the climate sensitivity to CO2 forcing in CESM2. And also, we wanted to run our cloud locking simulations both at high CO2 and pre-industrial CO2. And so having this 8x CO2 spin up allows us to explore the state dependency of this feedback. And then from our 8x CO2 spin up, we branch the runs and run 2 cloud locking simulations. So here we are imposing what the stratocumulus clouds are doing in those subtropical regions. We have a no strato case where we've completely removed the low clouds there. And then we have a strato case where we've imposed those very strong 100 watt per meter squared radiative forcing clouds. And then we do the same thing at low CO2. So we have a 1x CO2 no strato case and a strato case. And it's the temperature difference between these 2 cloud locking runs that will tell us what the global warming impact of a stratocumulus cloud breakup is. So interestingly, we found that the breakup only produces about half as much warming as we expected. So remember from that very simple calculation, you might expect up to 8 Kelvin, but we only saw about 4.5 Kelvin, both in the 1x CO2 and in the 8x CO2 cases. And this was pretty shocking to us. We didn't really know what to expect going into this project. And so the rest of this project was really trying to understand, why is the climate responding so differently to this localized forcing versus the CO2 forcing? And the way that we're going to get at these climate feedbacks is with the Gregory method. So here I'm showing you the net top of the atmosphere radiative imbalance in these simulations as a function of the change in the global mean surface temperature. And we've split the response of the climate system into 2 different timescales. We have a rapid adjustment phase, which is the first about 20 years of the simulation. And then that's characteristic of like the atmosphere's adjustment to the radiative forcing. And then we have a slow adjustment phase, which is more on the timescale of ocean adjustment to these forcings. And so the y-intercept of this rapid adjustment phase, when the surface temperature change is 0, this will give you the initial radiative forcing that this cloud feedback caused. So we were going for 6.5 watts per meter squared. We ended up more with about 6, and that's because there were high clouds in those regions that we let evolve that slightly minimized how much radiative forcing we did, but that's okay. We kept that in mind throughout the analysis. And then if you do the x-intercept of the slow adjustment phase, this will give you the equilibrium change in temperature because you're bringing the top of the atmosphere radiative imbalance to 0. And then, excuse me. And then to calculate the global feedback parameter in these runs, you just take the negative ratio of the radiative forcing over the equilibrium temperature change. And you can see that these global feedback parameters are much less sensitive than the global feedback parameters to CO2. And just to be absolutely sure, we also calculated the global feedback parameter to CO2 in our version of CESM2. And again, we see that the climate response to this localized forcing of the stratocumulus breakup is much weaker than to a more homogeneous forcing, like from CO2. And so in an attempt to understand this difference, we looked at the different climate responses in the slow adjustment phase and the rapid adjustment phase, and then we isolated the shortwave response versus the long wave response. And we found that the biggest difference was in the shortwave feedbacks in the rapid adjustment phase. And specifically what you can see here is that actually in the following a localized stratocumulus breakup, we actually had a stabilizing shortwave feedback, which was mitigating warming. Versus for the homogeneous CO2 case, there was a very positive shortwave feedback. And what we think is happening here is that here I'm showing you cloud cover as a function of latitude. We have these stratocumulus regions, and then we have some low cloud cover in the mid-latitudes and the free troposphere above. In the temperature in the free troposphere is very connected to the surface temperature in the low latitudes because of strong overturning circulation. And so when we remove the stratocumulus clouds, all of a sudden you're heating the surface in the low latitudes quite a lot, and this is inducing very strong convection. And so that heat is communicated to the free troposphere very quickly. And now when we're looking at cloud cover in the mid latitudes, the low cloud cover there is very correlated with the lower tropospheric stability. And because we're warming the free troposphere, but the ocean beneath the clouds has not yet had time to respond to this heating, you have a very strong increase in lower tropospheric stability here. And this allows the low clouds there to become much stronger. And so now, even though we have lost the clouds in the stratocumulus regions, we have built up low cloud cover elsewhere. And this is strongly mitigating the warming from the stratocumulus breakup. And so I'm demonstrating that here in our change in low cloud cover for our stratocumulus breakup runs on the left versus a CO2 forcing case on the right. And you can see that when you remove the stratocumulus clouds, you have an enhanced low cloud fraction elsewhere. And that's stabilizing the climate somewhat to this stratocumulus breakup. So I'll put my conclusions here. Thank you.
Andre. Very nice talk. I love this class feedback and analysis. Do people have questions, comments? Praise. Christy, would you like to ask a question or is that a coincidence?
No, I did want to ask a question. Hang
Okay.
on. Sorry, I just had to turn on my audio. So it seems like the most obvious application to this is to marine cloud brightening, right? So, if you play the whole thing in reverse and you can brighten the stratocumulus regions, that you're only going to get half the radiative response that you might expect, unless you do it everywhere. Any comments on that?
Yeah, I mean, I've seen a lot of interesting work thinking about, okay, is it better to do this marine cloud brightening in these subtropical stratocumulus regions versus, for example, in the Southern Ocean? I think that one weakness of our experimental setup here is that we basically had a branching from a simulation that had the model created clouds, and then we had a no strato case and a strato case. And I think that a more helpful way to actually look at marine cloud brightening is to actually take a fully strato case and then completely remove them, and so you could actually tell what the difference is. And there might be some non-linearity there.
Oh, we have Rob. Rob, go ahead, please.
Yeah, hi. Interesting talk. Yeah, following on from Chris Brotherton. We've done, there's simulations in which these three boxes have essentially been perturbed with multiple models. It's the RASH MCB protocol where they're all being brightened. And I don't recall seeing reductions of cloud, which you would expect the reverse of this in the mid-latitudes. But I wonder if you've looked at any simulations of that type of the MCB that have been taken, that have happened from other people.
No, we haven't looked at those yet. And another thing to keep in mind is that we ran these simulations in one model, and obviously different models will have different cloud feedbacks. I think, that's definitely something that is super interesting to us. But yeah, we haven't looked at it yet.
Yeah, very interesting. Thank you.
Sweet. So we have to move to our very last talk. Thank you again, Andrea, for the very nice talk. So our last talk will be from Sally Zhang. She's currently an assistant professor at University of Nevada, and she's going to talk about the tropical response to the Antarctic meltwater across models. Sally, take it away.
Thank you, Xia. Thank you for the opportunity. Oh, let me share my screen. Can you see?
Yeah. That's good.
Great. Awesome. All right. So now we're going to move to Antarctica and the Southern Ocean. And this is kind of a follow-up study on many Southern Ocean teleconnection works that I did earlier to look at the response to meltwater, and especially focusing on the impact in the tropics. So I'm just gonna put up the key results first in case you're in a rush and you have to leave early. But what we found in this study is really that if we look at multiple climate models and look at their response to Antarctic meltwater forcing, the response is pretty robust. So most models would produce cooling over the Southern Ocean that propagates into the tropics and even beyond. But the magnitude actually varies quite a bit across the models, maybe not surprisingly. And also most models show a northward IPCC shift as a response. We also found that models with stronger subtropical low cloud feedback tend to show a larger tropical to Southern Ocean cooling ratio, which we'll get into in more details. And at last, we did a surface energy budget analysis and actually found that the teleconnection pathway is quite different depending on the model that you focus on and also the basin, so the Pacific versus the Atlantic. Right, so the Southern Ocean teleconnection that can influence the tropical SSTs. And I think this has been shown in many different studies of various complexities. And I'll just highlight two examples here. The first one is what got me interested in this topic is the slab ocean model. When they make the Southern Ocean deeper, the mixed layer deeper, this enhanced heat uptake over the Southern Ocean can lead to cooling that not only is constrained over the Southern Ocean, but also propagates into the tropical oceans. And here we can see both the Pacific, actually all three ocean basins show cooling close to the equator. And then a second example is using fully coupled models. And these are the Southern Ocean pacemaker experiment, where we nudge the Southern Ocean SST to follow the observed cooling trend. And what we found is that if you look at the past 6 decades and forcing that Southern Ocean temperature trends, we can attribute to about a third of the cooling in the Pacific, tropical Pacific, to the Southern Ocean, and even more, about 2/3 for the tropical Atlantic. So these are, and there are more studies that support these results that the Southern Ocean can impact the tropical SSTs. So how does the teleconnection actually work? So this Kim et al. Study has a nice schematic showing the teleconnection pathway, which if you have a perturbation over the Southern Ocean, first these anomalies will get propagated via the eastern boundary current, via so number one here, the climatological advection of cooling. And these cooling will, along the way, gets enhanced by different feedbacks. And here we're looking at 3 different ones. There's the west feedback, wind evaporation SST, and the stratocumulus feedback, because this is in the region where actually one of the regions that Andrea showed earlier along the coast of South America. And also we have ocean response due to upwelling. So all these processes can help enhance the local cooling that eventually gets propagated into the tropics. And to get to these schematic, people usually use a surface energy budget framework. And so this is just a rendition of that. And we can linearize this equation, especially for the latent heat flux term, to diagnose the SST. So it's a diagnostic framework, and usually you would need to have a perturbation to tell you about causality, right? And in this case, we're perturbing the Southern Ocean. And we can diagnose the SST-driven trends due to short wave, which is largely due to clouds, long wave, sensible heat flux, latent heat flux, and ocean dynamics, usually diagnosed as a residual. So now let's move to talk about the Antarctic meltwater. And this is an emerging topic because studies have shown, and especially this more recent study by Kaufman et al., that in the historical period, it's estimated that Antarctic meltwater can explain about a third of the observed Southern Ocean cooling. And there are other contributors that can affect the Southern Ocean sea surface temperature, but it seems like the meltwater can be one of the important factors. However, and we know that Antarctic meltwater input will accelerate under climate change as ice sheets and ice shelves melt, but coupled models do not really include these processes, therefore omitting the meltwater-induced cooling effect. So here we're analyzing simulations from the SOFIA initiative under a very idealized but standardized meltwater forcing protocol. And here it's a time series kind of giving you a sense of how big the forcing is. It's really large. So we're focusing on this end water experiment highlighted in the black dashed curve. And the magnitude is kind of in between. So it's much higher than the more moderate scenario simulated by ice sheet models, but kind of half of the equilibrium of the high end scenario. So it's a very large forcing, and if you want a sense of want to get a sense of the comparison to historical meltwater input, those are shown on at the bottom. Those crosses are the estimates from the historical period, and it's much stronger than the historical forcing. So we have a very strong forcing to look at the response here. Right, so let's get to the results. Here, I'm showing the multi-model mean surface air temperature at the top and the precipitation at the bottom. And stippling is showing that 6 out of 7 models agree on the sign of the response. And for the temperature, you see overall really good agreement amongst models that even extends into the Arctic, this cooling. So in fact, only 1 out of the 7 models don't really give consistent cooling response in the equatorial Pacific. And if you're interested in the individual models, I can show that later too. But then in terms of precipitation, we also have very strong agreement of this northward ITCZ shift. So the enhancement of precipitation along the ITCZ in the equatorial Pacific. But if we look at the spread across the models, here on the right, I'm showing the zonal average temperature and precipitation response. There's actually quite a large spread. And the largest spread in the temperature is actually occurring over the Southern Ocean. So models vary between about 1 Kelvin to 3 Kelvin cooling over the Southern Ocean. And that spread gets smaller in the tropics, but also you could notice that the models with the strongest Southern Ocean cooling don't necessarily have the strongest tropical cooling. And same for the Arctic. Actually, here, for example, the green curve shows the strongest Arctic cooling, but the Southern Ocean cooling is actually quite weak. And then for the precipitation, it's also very noisy. I guess it's not surprising that models vary in their precipitation response. They all have this increase in the Northern Hemisphere, north of the equator, but the decrease to the south really varies in location. Some occur north of the equator, some occur south of the equator. And this is not simply correlated to the climatological precipitation that we have checked. Right, so we have found a very large model spread, and in particular, we're going to focus on two kind of metrics or regions. One is in the equatorial Pacific. So this is on the left showing a longitudinal plot of the Pacific surface air temperature response. And the black dashed line is the multimodal mean. So we're looking at the zonal gradient across the Pacific. While most models show stronger cooling on the eastern side of the Pacific Basin, this is not the case across all models, and also the magnitude vary a lot. And then the lighter colored lines are showing the different ensemble members for some of the models. So this region is of particular interest, I think, for this community. It's related to the pattern effect. So we want to focus a bit more on this region. And another one that we're looking at is for the Atlantic. So now we're looking at the meridional gradient. So it's a plot across latitudes, looking at the surface air temperature response across models. Again, there's a very large spread. The gradient, so this dipole response over the tropical Atlantic has implications for tropical cyclone and Sahel rainfall variabilities. So we'll also focus on that a bit next. So we can calculate kind of two metrics based on these two regions. One is the zonal temperature gradient. So here is defined as the red box minus the blue box in the Pacific. And we can show that these models show a very large spread in these Pacific zonal temperature gradient. And they're actually positively correlated with each model's subtropical low cloud feedback, so the shortwave cloud feedback. And we also put where the observed estimate of the feedback strength in the Southeast Pacific subtropical low cloud region. For the Atlantic, the correlation doesn't look as strong. So we're plotting the Atlantic meridional dipole, which is the difference between, again, the red and the blue across the tropical Atlantic. And we see also a very large spread amongst the models that's not very well correlated with the shortwave feedback strength. However, if we normalize both metrics to their Southern Ocean cooling response, we actually have an even stronger correlation for the Pacific, and now we have a much more robust correlation in the Atlantic as well. So because there's such a big spread across the models in their Southern Ocean response, we feel it's fair to calculate these tropical metrics as a ratio to the Southern Ocean cooling. And in this way, we can say that the multimodal spread, the intermodal spread of the shortwave feedback strength can explain the majority of the spread of the tropical Pacific response, and also about 60% of the Atlantic meridional dipole spread. And the last step is to really look at the teleconnection pathways and to see how the models differ in the response. So first, we focused on CSM2, which, if you remember from the previous plot, has the strongest response, also the strongest low cloud feedback. So we can take the surface energy budget and calculate each term for these three boxes highlighted in black. So we have an Eastern Equatorial Pacific box and then a Central Equatorial Pacific box. These two regions actually have very different surface energy budget compositions. And then we are also looking at the tropical South Atlantic. So the difference in analysis here, we're actually calculating the time series for the full 100-year simulation. So we can look at the evolution. And what we found is that the evolution, the initial evolution tends to be different from the equilibrium response depending on the region. But in this case, for the equilibrium response, the three regions have different contributors from the budget. So for example, the Eastern Pacific, we have the shortwave dominating and then the latent heat flux. But for the tropical Atlantic, it's mostly latent heat. And if we look at a different model that's moderate in its shortwave feedback strength, the composition again is quite different. So for the Eastern Pacific, it's still it's mostly coming from latent heat, but shortwave is also really important. Whereas for the tropical Atlantic, both latent heat and shortwave are important for this model. So now we can also compare the equilibrium budget composition to the first 5 years, which was used to kind of create this teleconnection pathway. And we can see that the terms don't always show consistent compositions, especially for the tropical Atlantic. So again, there's a difference between the Pacific and the Atlantic, and then there's also a difference between the two models. So this is really motivating us to revisit the surface energy budget in more models possible to carefully examine the teleconnection pathway in both basins in the near future. Right, so this is the summary, and our paper actually just received reviews this morning, so it will revise. I'm happy to take any feedback from you guys. Thank you.
Thanks, Sally. Very nice talk. Question. Andrew.
Hi, Sally. Thanks for the great talk. Do you maybe I misunderstood, but did you show that the GISS model had like worms in the tropical Pacific? Do you have a map of that, or do you have some? That seems very counterintuitive to me. Do you have any idea why that happens, or?
Yeah, so GISS model was the outlier. So you can panel K is showing the air surface air temperature response there, and there is some cooling out of Eastern Pacific in the tropics, but there's actually warming over like around the dateline. So we actually haven't dived into this particular model, but it will be interesting to look at its energy budget to see why the central equatorial Pacific it's showing a warming. It's really the only model that has this signal.
Can I just ask you a quick technical? How much time are you averaging over for these plots?
We're averaging over 50 years.
Okay, cool.
Yeah,
thanks.
Last 50 years.
David, go ahead, please.
Yeah, two questions. One is, what was the distribution of the water that you put in the Southern Ocean? Was it zonally uniform? Was it regionally dependent? The second question is, have you looked at how the results stratify when you stratify the strength of the double ITCZ in the problem, which really determines, I mean, the strength of the shortwave cloud feedback in the Southeast Pacific is highly related to whether or not you have a double ITZ or not. So I'm just wondering if you'd actually looked at that.
Yeah, so the first question, so the forcing is along the Antarctic coast. So so we add the fresh water along the coast of Antarctica. Does that answer your question?
Yep.
Yeah. And then for the double ITCZ, so far I've only looked at for each model, their climatological precipitation distribution, and to see if the response is kind of correlated to that climatological distribution. And we actually didn't see anything consistent. But I don't think we have looked particularly at the double ITCZ bias, whether that gets eliminated or reduced in these simulations. But that's a good suggestion.
Yeah, I always thought that if you, the stuff I did with Yue Dong is if you do this in a flux corrected model, you get a much stronger response. And I think it's simply because you remove the double ITCZ, so you have a stronger stratus deck. And so you would get the results that you kind of see here. And, of course, the question is, why is there a double ITZ, which is a question that's been on the books since I was a graduate student 35 years ago. And maybe that is also related to the subtropical stratus decks. But I just wonder if when you say compare that to the climatological precipitation, if you just focus on whether or not there's too much rainfall south of the equator in an ITCZ, I'm just wondering if that shows up, is strongly correlated with your results.
Yeah, we have not looked at it, but I'll probably follow up to do some additional analysis with respect to that. Thank you.
Great. Let me know what you find out. I'm
Yeah.
curious.
Yeah, I will.
Well, we have reached to 1 hour. If people still have questions for Sally or another two speakers, feel free to stay a little bit. Otherwise, I would like to give another round of applause to our three amazing speakers today. And thank you all for showing up for our last event this year. And we will continue our events next year in January. And we'll see you next year. Take care and enjoy the holiday season.
Thanks for the nice talks.
Thanks to the organizers.
Bye, guys.
Thank you for organizing.
Merry Christmas.
Merry Christmas. Cool.